So everyone, it is my pleasure to introduce to you our colloquium speaker tonight, Doug Lombardi. Dr. Lombardi is an assistant professor of science education at Temple University in Philadelphia. He recently finished his PhD in science education, not in science education, in educational psychology from the University of Nevada, Las Vegas, where he studied the nature of conceptual change, in particular hot conceptual change related to climate issues, related to global warming, related to global warming, as we've talked about sometimes. And so Doug will be giving us a research presentation based on his dissertation work, which of course is available to you on ProQuest if you'd like to read it in great detail. I've had the privilege of knowing Doug for, Doug, I think almost 10 years. Doug and I first met when he was living in Tennessee, and he came to a workshop that we were running for the University of Hawaii called TOPS, Toward Other Planetary Systems. And Doug and I struck up a great friendship. He moved to Tucson for a while I was at the University of Arizona, where he was working for the NASA Mars Phoenix mission as the education lead there, and did some fantastic work, and is well known throughout NASA for breaking some rules and coming up with some fantastic ways of doing education and public outreach. We're in for a real treat tonight, and so it's my pleasure to introduce to you Dr. Doug Lombardi.
All right, thank you, Tim. I appreciate that, and I just want to formally say hello to everyone, and I do want to thank Tim for inviting me, and also you should know as Tim's students that Tim is a great mentor and a great support during the whole process of this whole search for an academic position, if that's something that you choose to do. He was a tremendous help for me, and I greatly appreciate it, and I greatly appreciate your interest in the topic. So just looking at this title here, we're going to talk a little bit about climate change. We're going to talk about these notions or conceptions that people have about it. And I'm also going to talk about critical evaluation, this idea of plausibility, which is of particular interest to me, and plausibility reappraisal, and then knowledge reconstruction, which is kind of one way of looking at conceptual change. So just as a quick roadmap of where I'd like to go tonight, I'd like to give you a quick background on conceptual change and plausibility. And then I'm actually going to talk about 3 studies, not just my dissertation study, but a program of research that I had the opportunity to develop as a PhD student at the University of Nevada, Las Vegas. At the end, I'd like to talk just kind of overarching about some of the implications of this research program for instruction, STEM education, and future research. So I guess what is conceptual change? And I'm going to give you my viewpoint on it. It's really a special case of learning. We know that background knowledge is essential to learning many topics, or essentially any topic, but in the case of conceptual change learning, what happens with background knowledge is you have a conflict between the background knowledge and incoming information. And in the case of science education, it uses the topic as science related. And conceptual change involves overcoming this background knowledge, as opposed to we use the background knowledge, but it's not as much of a benefit, seen as much of a benefit by many conceptual change researchers and those that teach about conceptual change. And science is a particularly kind of verdant field for conceptual change because learners have many incorrect ideas about how science operates and about the universe at large. So this kind of very busy diagram kind of gives the perspective that I come from on how conceptual change is developed. It was originally, this diagram was originally thought of by Dole and Sinatra back in 1998 in association with their cognitive reconstruction of knowledge model, which is a conceptual change model that includes a lot of what Tim calls these hot constructs of motivation and affect and emotion. And conceptual change really has a philosophical underpinning, really 2 kind of branches to that. One's this philosophy of science that emanates from the Kuhnian perspective, kind of this notion of how science has undergone change. And then there's these psychological learning kind of philosophies of psychological learning. And of course we get ideas about assimilation and accommodation from Piaget, where accommodation really relates to conceptual change. And we get to this idea of constructivism, where students construct knowledge mentally. But there's also a social cognitive aspect that Dole and Sinatra didn't include. And so I've included that on there. You can see that in the upper right, that social cognitive model in there. And essentially what that is the interactions that we have with individuals and culture that kind of shape how we develop our concepts and how we do conceptual change. So conceptual change research has progressed. Really, and early on when they were doing conceptual change research 40, 50 years ago, it looked at this developmental changes in young learners' knowledge and just kind of what naturally occurs as we develop and grow older. And then there was the cottage industry of conceptual change, which kind of emerged in the 90s and early 2000s of kind of this cottage industry of developing what are the misconceptions, cataloging misconceptions, what are they? And it was kind of this industry that really went into vogue, and it's somewhat less de-emphasized, although it's still a very important area. And there was a seminal work that kind of really changed a lot of the modern conceptual change ideas that was done by Pintrick, Marx, and Boyle in 1993. And basically it says that conceptual change is not just a matter of this cold, rational thinking process, but it involves motivation, it involves social interactions, it involves the history of the individual, their prior experiences a lot more, and it's kind of this hot model of conceptual change that we're looking at now. Now, I'm particularly interested in conceptual change and plausibility, and what happened is I was taking a seminar in my doctoral program on conceptual change, and Gail Sinatra was leading the seminar. She turned into my advisor, and one of the things that struck me from Gail's research was that plausibility, it kept cropping up in all these conceptual change models, but nobody had really studied it. Nobody had studied it empirically. It had been theorized, and I thought this is a great opportunity for me to look at it. And it's really turned out to be a very productive area. So in conceptual change situations, I view plausibility as a judgment on what I call potential truthfulness. It's not a full-blown belief or an epistemic commitment to something. What it is it's a maybe. And it occurs when you have comparing two propositions. And in the conceptual change situation, it might be when you have incoming information and an existing mental representation. So this idea of alternatives is very important when you're making a plausibility judgment. So as I alluded to earlier, conceptual change is really involved with plausibility in so many levels. There's the classic conceptual change model of Posner et al., which views conceptual change as kind of this linear, sequential process. And plausibility, the message, the incoming message has to be plausible at some point before conceptual change will occur. There's kind of an alternative to this knowledge reconstruction that I've been talking about a little bit. It's called knowledge in pieces, where knowledge is viewed at a much smaller grain size, where we have these free-floating knowledge elements going around, and eventually what we try to do is construct them into a scientifically accurate conception. And the glue of this construction, according to the CESA, is mutual plausibility of connection between these elemental pieces. On the other side of the debate of conceptual change is this notion from Mickey Chi, which looks at ontological shift, where we have these broad categories of knowledge and thought. And what defines an ontological category, or a category of what is this notion of plausible attributes. So for example, if climate change is a process, we would never refer to the color of climate change. That's just not a plausible attribute. And finally, there's this Dole and Sinatra model, which has kind of kept plausibility in the frame of Posner et al., but currently is undergoing modification due to the research that I've kind of been leading, and others have been involved with that. So just quickly, before we get into the actual research, plausibility, when you're exposed to scientific claims, you make mental representations, you connect these mental representations to your background knowledge, and you do evaluation of these connections as a plausibility judgment. So through this program of research, this did not come out at the beginning. This was a theoretical model that I developed as part of my dissertation, and I'm now currently writing up, that kind of developed from some of the empirical pieces that I've had and some of the literature review that I did. It was really a nice guiding element to my literature review. And essentially, I'm going to focus on these elements, but I just kind of want you to take the broad picture. This is just a kind of a standard engineering, one feedback loop type of model if you look at it. You have information coming in, it results in some kind of potential for conceptual change, and then you have the potential or the possibility of reappraising that plausibility judgment. So just zooming in on that model, it's initiated by what we call anomalous incoming information, and it's pre-processed. That information's pre-processed really on kind of these four factors that I've looked at. Corroborative alignment, how well does it connect to our prior experiences? Information complexity, if information is very complex coming at us, it seems less plausible. Perceived conjecture, if for some reason we see the source as making something up, we'll see that as less plausible as well. And then there's these heuristic rules, these automatic implicit cognitive processes that go on that we're not even aware of, biases that we have that may influence our plausibility, just the initial kind of source indexing of that. The actual plausibility judgment in the center case is where you make the judgment, but it depends on these factors, this degree of evaluation, and things like epistemic motives and disposition. That's our inclination towards knowledge and our beliefs about knowledge, kind of are these semi-permanent, stable conditions that we have. It depends on our motivation, how actively we engage with the information. And then there's this notion of topic emotions, which are emotions specific to a topic. It's really relevant to climate change, where we may like the topic of science in general, or excuse me, we may like science in general as kind of a domain, but we may not, we may be angry about climate change. So we have a kind of a specific topic emotion. And again, this is either done implicitly, and often probably is, without our conscious thought, or it can be made explicit, and that's hope for us as science educators, because we bring this plausibility reappraisal and this evaluation up to the forefront of our minds, and we really kind of mold it, and then we can see what happens to it. And then, of course, it's a simple kind of proposition. What happens with conceptual change? Well, if the plausibility of the incoming is greater than the plausibility of our background knowledge, then we might have a strong potential for conceptual change. It doesn't mean conceptual change will happen, but it means that it may happen. There's a weak potential if it's about the same, you know, they both sound plausible to me, and no potential for conceptual change if the plausibility of the incoming is less than the plausibility of the background knowledge. So let me take a focus on kind of these three studies that I've done and how they fit into the development of the model and how they've kind of worked on my thoughts on plausibility and conceptual change. So the first study was one that I did again as a PhD student. It was a study where I just wanted to look at empirically, is plausibility related to conceptual change? And it involved undergraduate students. They were enrolled in geoscience courses. One was a course completely devoted to global warming. The other was a physical geography course where there was just a brief discussion of climate change and weather. And what we measured was overall plausibility perceptions about climate change, and I'll talk more about how we measured this in just the next few slides. Knowledge of weather and climate distinctions, which is kind of the knowledge piece here, and then deep time understanding, which is a kind of a more related, broader, kind of a threshold concept that is so important to many scientific disciplines. So how do we measure plausibility perceptions of climate change? Well, this is really rather a simple instrument. What I did was I took there were 8 major statements in the IPCC report. That stands for the Intergovernmental Panel on Climate Change that was submitted in 2007. It was the 4th major report. It's the last major report that's been done. And what I did is I tried to keep those statements as organic as possible. So I didn't change them much, and then I just had individuals rate these statements, you know, from greatly implausible 1 to highly plausible. 3 of the statements related to scientific evidence supporting climate change, 2 related to linking these changes to human activities, and 3 related to predicted impacts of future climate change. So here's some example of those IPCC statements. For example, the evidence of change, you can see on there, you can read it. the link to human activities, and these are essentially how they appear in the report. Some of the jargon has been reduced, and then potential impacts. Take a look at that potential impacts one a little bit closely, because that'll be an interesting kind of, as we do the summary at the very end of our talk. And you see the plausibility of that and how that's manifested itself over these various studies. Of course, we're interested in misconceptions as conceptual change researchers. There's been a lot done on climate change. They fall into two broad categories. Some are evidence-related and some are cause-related. And so cause-related would be that climate change is caused by stratospheric ozone depletion, and that results in significant increases in global temperature, which is inconsistent with the scientific understanding. An evidence-related one, though, is that short-term and local weather events are evidence of climate change, and this is the one that I chose to kind of focus in on. It was a very simple instrument. Again, there were several statements that students just classified as either climate or weather. And these are examples of some of those statements. If you look at those statements, it's not just merely precipitation, it's not merely temperature, but we also try to explore the full kind of construct of weather and climate. For example, winds and fires and glaciation. And to look at deep time, we used an instrument that's been used fairly extensively in the biological evolution education research, which is an instrument that's an open-ended, basically an open-ended scale on deep time developed by Dodick, and Orion. So what did we find in that study? Well, this is kind of it's what we call a hierarchical regression model. So if you look at this, this square over here is basically taking out for the existing background knowledge. So we kind of statistically controlled for their existing background knowledge. Of course, that explains a lot of their understanding of knowledge of weather and climate distinctions post. So the pre-knowledge explains a lot of the post-knowledge. No big surprise there. But once you take that out, deep time understanding accounted for an additional 6% of the variance in their understanding of weather and climate distinctions post-instruction. And plausibility perceptions, lo and behold, accounted for an additional 5%. Now that doesn't seem like a huge amount, but it was enough to really get us going. It was a significant result, and it was important because it really was one of the first studies that's been done to look at the connection between plausibility perceptions and understanding and change, really. And this is an example here of what happened between the two different classes. Really, both of them changed their understanding of weather and climate distinctions. The kind of the take-home message there is that even a little bit of instruction about weather and climate distinctions, and you'll notice that I've abandoned this instrument as I've gone along, because it is basically, once people get what weather and climate distinctions are, they've got it. It doesn't really take a lot of instruction for that. So it's really not one of the more complex topics in climate change. We almost had a little bit more gain though with the global warming class, but not enough to really to go out and say we had a significant interaction there. So in my second study, I wanted to look at what happens with developing this plausibility judgment, and I specifically looked at these dispositions towards knowledge, these epistemic motives that we have, this need for closure, this need for cognition that we have, and topic emotions. I did not look at motivation in this study. This involved teachers, in-service science teachers and pre-service elementary teachers, and I measured topic emotions about climate change and teaching about climate change. I used the same instrument for plausibility perceptions about climate change that I used in the first study. Remember the 8-item instrument. Measured weather and climate distinctions again, and then I measured these need for closure and need for cognition. Basically, essentially, need for closure is an epistemic disposition to find quick solutions to knowledge in unambiguities, like, well, I don't like this uncertainty of climate change, so it must be wrong. You know, it must be bad knowledge, kind of thing. Anytime knowledge is uncertain, you have a disposition. If you have a disposition towards a need for closure, you're going to want to make a quick decision about the knowledge. And essentially what I did then is look at the relationships among these. This wasn't really a full-blown conceptual change study, though. So this was more of a simple regression. What predicts the plausibility perceptions? It's correlational, but it's a little more directed towards that. It gives us a little more information than just direct correlations. So what we found was we kind of divided emotions into two topics. One was the topic of emotions that specifically dealt with the emotions that teachers have about climate change and then about teaching. So model one was emotions about climate change. And what we found is that anger, if they're angry about the topic of climate change, that predicts their plausibility perceptions. As a matter of fact, it has a negative relationship. Interestingly, hopelessness also predicts plausibility perceptions, but in this case, the more hopeless you are, the more plausible you think climate change is. But that's an interesting aspect. It's considered a negative emotion, and for a teacher to be hopeless about a topic means that they may not teach that topic, for example. And the more knowledge one has, it seems the more plausible it is, and hopelessness is involved with that equation. Looking specifically at topic emotions that relate to teaching about climate change, again, anger is a significant predictor again. The more angry you are about teaching about climate change, the less plausible you think climate change is. Not a huge surprise. But then this epistemic motive of decisiveness. If you want to make quick decisions about knowledge, you want to be decisive about what knowledge is, that's a negative relationship too. So the more decisive one is as a dispositional element towards knowledge, the more, or less, excuse me, less plausible climate, the less plausible they view climate change. And I see we have a question there. Ken, go ahead.
Can you explain the unexplained, please, in the last two paragraphs?
I cannot explain the unexplained. It just doesn't work that well. I mean, you know, education research is just a little bit messy, so there's other factors that are explaining their plausibility perception. So perhaps it's their motivation to engage with the topic, or perhaps it's some heuristic or bias they developed, or things like that. There's a lot of areas that it could be, but I don't really know what that is. Does that make sense, Ken? The good thing is it gives us a little job security to think about it a little bit more and maybe figure out what that is. Ken, you got another question? Or are you good to go? This was a mixed method study. I just didn't collect survey data, but I also did teacher interviews, and this is an example of a connection that I saw between, by doing a thorough content analysis, between plausibility and anger. The teacher Millie here, that's a pseudonym, she was reflecting or thinking about a recent report that she had heard about, that she was actually thinking about the IPCC report and a news article that came out about it, that there was an error in it. And she equated that with lying. Oh yeah, the scientists lied about it. She was really angry about it. You just discredit yourselves. So she's associating anger and plausibility. She thinks that they're much less plausible. She thinks they're liars because of the mistake in the document. So for my dissertation study, which was study 3, and then I'm writing it now, what I'm really interested in as a science educator and a science education researcher is how to get a learning environment where we can reappraise plausibility judgments. And the way to do this, I'm thinking, is through what I call critical evaluation. So what is critical evaluation? Well, it's looking at the connections between evidence and a model, but not only between evidence and the scientific model, but evidence between a model and an alternative, and doing that essentially at the same time. So critical evaluation may promote higher quality plausibility judgments because it's really a metacognitive process. You're thinking about the connection between the data and the evidence, and you're weighing how that works. And you're also coordinating theory and evidence, which according to Kuhn and Pearsall is really an aspect of scientific reasoning. That's what scientists do when they reason, when they're reasoning about their topics of research. They don't always do it. So work with middle school students. As you kind of see, I'm kind of looking at not only just one age group here. I'm not just looking at undergraduates. I'm not just looking at adults as teachers. I'm not just looking at students. This involves students, but I'm trying to look at a whole broad spectrum to see how this plausibility judgment plays out. This was a quasi-experimental design. Quasi-experimental means that I didn't do a true experimental design by random selection. I had 14 classes that I was invited into at a middle school. It involved 4 teachers, and I trained them on how to do the treatment activity, and then we also talked about their normal curricular materials, which is they used Investigating Earth Systems, which is a very good curriculum that matched very well with the topic that we were looking at, which was climate change. 7 of them were in the treatment, 7 were in the comparison. And we looked again at plausibility perceptions, but we also looked at these other things, which I called model plausibility and correctness. I'll explain that in a little bit. And then I wanted to develop a more robust instrument over the distinctions between weather and climate, and I called this new, more robust instrument the knowledge of human-induced climate change. So essentially, here's kind of the procedure. It involved 6 class periods. The students got some instruments in over 2 class periods. We didn't inundate them all at once with all these surveys. Then they experienced the treatment activity in 2 roughly 45-minute class periods, and then we gave the instruments at the end. The teachers did all of this work. So what was the treatment activity that promoted critical evaluation and plausibility reappraisal? Well, it's this thing called a model evidence link diagram. And essentially what it is you have 4 lines of evidence these are very important lines of evidence for climate change. And you have 2 models, one which is model A, which is our current climate change is caused by increasing amounts of gases released by human activities, which is the scientifically accurate conception. And then model B, which is our current climate change is caused by increasing amounts of energy released from the sun, which is a very popular skeptic model. And what the students do, and I'll show you an example of student work, is they connect each evidence to each model. So you're wondering, well, how many arrows are going to be on this thing? Well, there's going to be 8. And they draw a different type of arrow depending on the strength of the evidence in relation to the model. So for example, if a student thinks that evidence 1 supports the model, they'll just draw a regular arrow. If they think that evidence 3 strongly supports model B, then they'll draw a curved arrow right here. See that curved arrow? And I'll show you what this looks like in just a second. Well, how do the students learn about these evidences? Well, it's a pretty simple task. They look at these evidence texts. They read a 1-pager for each evidence. It involves a little bit of information and involves some graphical representations or some figures. So this is an example of evidence 1. Both the treatment and comparison used these. Now the comparison group was doing their normal activity, but what they weren't doing, and I'll just go back just a second, what they weren't doing is they weren't considering 2 alternatives. They were just considering the connection between evidence and the model that they were predicting for climate change. There's evidence 1 text, there's evidence 2, evidence 3, and evidence 4. And here's an example of a student student work that what they did on this. And they adapt to it pretty quickly. There's a little bit of upfront work that you have to do with the students. And then we measured what we call perceptions of model plausibility and correctness. One of the important things to look at, remember that result of the plausibility judgment, that potential for conceptual change? Remember that one conception has to exceed another for conceptual change to occur. Well, I actually wanted to measure that, so it's a simple measurement. The students pre and post circled the plausibility of each model. They were introduced to the models pre, and then after doing the MEL, they circled the post, and then the comparison group did it pre and post as well, in a very similar fashion. But I also wanted to look at the tie between plausibility perceptions and a more full-blown epistemic commitment, a more formed belief about which one they thought was correct. So I made them commit a little bit. In this, they just circled 1, either very certain the model A was correct, very certain that B was correct. The students also did a an explanation task, which I've done a qualitative analysis on. I'm not gonna, in the interest of time, I'm not going to get into that in great detail. I'm actually still kind of working on that piece a little bit. Qualitative analysis can be very time-consuming because you want to make sure you get it right. You want to make sure you're getting the right inferences. You want to keep checking yourself to make sure that your biases aren't influencing it. And this is an example of a student work on the model explanation task, and you can see this particular student work on their judgment at the end about the plausibility of each model and then model correctness. So what were the results? Well, before I get to the results, let me talk a little bit about how I measured knowledge of human-induced climate change. This is a little more robust scale. It was a 5-scaled Likert survey. There were 34 items on there, and 6 items specifically probed conceptions about causes of climate change. One, which is the scientifically accurate model of human-induced, and then the others are documented in the literature misconceptions. And the reason this works into knowledge as opposed to a belief is the students rated the degree to which they think climate scientists agree with the following statements. Now, there's very strong agreement. That's been documented extensively in the literature by a few people that climate scientists, those that are actively engaged in climate science, that 97% of climate scientists agree with the human-induced climate change model, for example. So if students don't think that climate scientists, if they think that climate scientists think that climate change is caused by increases in sun energy, they're pretty much wrong. So here are the results. And just kind of interpreting, what we have is the treatment group in blue, the comparison group in gray. We have what we call a moderate effect size, which is the effect size is how much you can actually attribute to practical significance, say how much you can actually attribute to the treatment. And that's a nice moderate effect size, which we don't often see in this kind of research, especially with such a short intervention. And you can see that there was quite a large increase, almost a 2-categorical increase in students that engaged in critical evaluation in reappraising their plausibility judgments. Now, was that associated with a change in which knowledge that they thought was, model that they thought was correct? Well, absolutely, it almost mimicked it exactly. This was actually a large effect size, 0.12, and again, a 1-category increase. But remember, we went from 2 categories. There was a question about this. Is this decrease statistically significant in the comparison? No, it's a flat line. That means that the comparison was the same pre and post. There is a significant difference here. There's no significant difference between pre and post at the precondition. Actually, there's no difference between the treatment and comparison at the precondition. So, but remember, again, back to the perceptions of model correctness, that was only a 5-category scale, and we saw a category shift there. Lo and behold, we saw changes in knowledge. Actually, quite a nice change. Again, a moderate effect size, and I don't have really time to break this down, but I will, I believe, show a figure that gets exactly into those misconceptions, and here it is. This is a conceptual change score. So essentially, this is the scientific model, and you can see the treatment group had a statistically significant change. That's what this asterisk stands for, in their changing from their ideas, and this is basically their relative change from 0 to 0.4, 0.4 more understanding, 0.4 units of understanding is how we would quantify that. But you'll also see that there was really the only other significant change was this amelioration. That's a reduction in misconception. So for some reason, students got the idea that, hey, this climate change is not caused by Earth changing its orbital pattern and getting closer to the sun, which is a common misconception. There were some other close ones, but that was basically about it. And actually, and another interesting thing is there was almost a statistic increase in the misconception amongst the comparison group that climate change is caused by increasing amounts of dust in the atmosphere. One of the instruments that I looked at in all 3 studies was this plausibility perceptions measure. And so and I remember I've worked with undergraduates, I've worked with teachers, I've worked with middle school students. And it turns out their plausibility perceptions are basically about the same. This is all their before any pre-activities or pre-learning at all. And you can see that scientific evidence supporting climate change is generally more plausible than predictions of future impacts. And this one here with the least plausible notion, which most people think is basically implausible or trending towards implausible, is this notion of the tipping point, that we've gone beyond into irreversible impacts. So that's kind of a nice little kind of study against all of that. And Tim, I don't know if Tim talked about the pre-prim, you can't make something from nothing, so you need dust. Maybe the pre-prims are involved in this. I would say probably maybe there was some more robust conceptions forming, but they can't say definitively on that. Tim knows I'm not a knowledge in pieces guy. So what are the implications for instruction? Well, it's this idea of facilitating a scientific habit of mind through what I'm calling, I've adopted this term, epistemic conceptual change. And that's not just changing a concept about a scientific topic or a scientific concept, but it's about how knowledge is formed scientifically. And the idea here is potentially, if we use critical evaluation in the classroom of alternatives, when we consider alternative explanations in the classroom, not just the scientific model, in a mode of critical evaluation, we can promote explicit plausibility reappraisal. And the reason I'm advocating this pushes beyond the tentative nature of scientific knowledge, which is an important nature of science elements. They've talked about that for years, but it's not just going that scientific knowledge is tentative, but there's an evaluation mode that scientists use to say which knowledge structure, which alternative, which theory, which model achieves a status of scientific validity. And by doing this, as students engage in this, they learn the practices of science, engineering, mathematics, and I've included the framework for K-12 science education in there because they talk quite a bit about evaluation, but they also talk about it in STEM education and mathematics. So this may have a broader appeal than just scientific topics. One of the things that it may relate to is social scientific issues, which are these issues of very much importance to our society, like climate change, for example, that also have a strong, strong content. But critical evaluation may be essential in this case, and it may be particularly important for these places where we have a plausibility gap. And plausibility may occur in situations beyond conceptual change. It may occur in other learning situations where you're just considering alternatives. There's not a lot of background knowledge, but there is a situation where you're presenting someone with cognitive dissonance. So we can talk more about that, but I don't want to go into great detail right now. So what am I doing? Done this work? Where am I going with it? Well, the first thing I'm looking at right now is this notion of the source, because there's not a lot of empirical evidence tying it into the plausibility judgment. I'm working on a study right now that I've developed with some researchers at USC, and we're looking at this notion of what we call source reliability, and that may actually change to source validity because we're having a little bit of problem developing this construct of source reliability. The notion of source reliability came from the philosophical world of Nicholas Rescher, who's an American pragmatist, who's written extensively about the plausibility judgment and abductive reasoning. Another question that I've got is how does this critical evaluation and judgment reappraisal develop? Can elementary students do it, for example? Maybe. Can they do it in the primary phases? Probably not. Can they do it in grade 5, grade 4? Potentially. I'd like to check that out. How does self-regulated learning impact the plausibility judgment and the plausibility reappraisal? What other instructional methods promote critical evaluation? We've talked about the model evidence link diagram, but there are others that are better. And then developing this climate education research community, which is just kind of in its infancy. More and more people are looking into educational research related to climate change, and I'd like to keep fostering kind of the goodwill amongst those folks. So I see I have about 43 more seconds before my 40 minutes are up. So I will just say thank you, and I'd like to open it up for questions, because I'm sure that I left something out by going lickety-split.
Doug, can you talk more about epistemic change? Because I'm having a little bit of trouble understanding how we might apply it as we're doing our teaching and learning.
Right. So the question really arises about views on how knowledge is, what knowledge is and how knowledge is constructed. So for example, someone may view knowledge as kind of this absolute truth, that there's this absolute knowledge that's in existence. There's these rules that are absolute, and that might be an idea of what we would call kind of absolutist thinking. Others may view knowledge as any knowledge is correct. You heard it. You've seen it on the Big Bang Theory, right? Where the big guy, Penny's boyfriend, who's not a scientist, he's the huge guy, comes in and he says, oh, I like to talk about science because there's no right or wrong answers in science. Well, of course there are right or wrong answers in science. There's a way that we evaluate that information. So the more advanced thinking about scientific knowledge is that this mode of that scientists evaluate information. They create these theories, these knowledge structures based on this mode of evaluation. Now, an individual scientist may not do it, but the scientific community at large goes through this process. So the change there would be going from an absolutist standpoint of sure and absolute knowledge to knowledge is developed through this scientific process of evaluation, collecting evidence, collecting data, connecting that data to our theories, and then evaluating alternatives based on that. So Debbie, I see you have a question about the demographics. Which study are you interested in?
Well, Ted asked about how he would love to see this done at Oral Roberts, Liberty, and and others. And Andrea asked also the same question, but I guess what were the
Yeah, I would like to ask what region of the U.S. the study was done in.
Great. All of these were done in the Southwest United States, in what I would call a neo-libertarian area. That's Las Vegas. So that's kind of the political stance. There was a large amount in the undergraduate study and in the middle school study. Actually, in the middle school study, it was majority minority with Hispanic students, and this was not a high quality or a high performing school, is the way I would say it. This was a school of normally that you would associate with lower academic achievement because of the socio status of the students. So it did work there. But yes, we'd like to try this in other regions of the country. So if anybody has interests, I'd be interested in talking to them about that. So Tim, did you ask about the theoretical framework? Is that Tim that asked about that?
Yep, that's me.
Okay, so I developed my theoretical framework, Tim. So that's what this model is. It's a socio-cognitive model, is the way that I would describe it. So that's the broad meta way I would look at it as a socio-cognitive model, and so it's very much has a strong cognitive constructivist component, but also this reappraisal loop in particular has a sociocultural. I think that's reappraisal has to, or most often has to occur through a sociocultural process. And sociocultural is broadly defined here as an individual. They may be talking to other individuals. They may be talking to a book, through some kind of dialogue and discourse with a book, a video, something like that. So the theoretical framework is my model.
You said on one of your slides that you feel it's important that students critically evaluate alternative models. And one thing I'm having a hard time wrapping my head around is that, for example, in the case of intelligent design, it sounds like you're advocating that students should be shown intelligent design in the classroom and learn how to learn how the evidence supports or doesn't support it. While I've heard from many science educators that they don't want intelligent design in the classroom at all because they think that that will give students the wrong idea and make them think that it is scientific. So I'm just looking for what you thought about reconciling those two viewpoints.
Yeah, I'd like to take a look at that. Gail Sinatra, who I worked with on this, has done a lot of work in biological evolution. She does not want me to do this. She's of the mind that we should not consider alternatives because of what you're saying, you know, particularly this notion that intelligent design and have such a strong foothold. I'm of the and I know that's a little bit different than you're going to hear from a lot of people, but I really think that there's reasons for this. Not just the mode of critical evaluation and learning the correct concept, but what it does is that there's motivational aspects to it, there's emotional aspects, and what we found, and there's more work to be done here, but I've written some of this stuff up, is that topic emotions are dampened through this critical evaluation. The adverse topic emotions of anger and frustration are dampened through that. A classic example is the Pluto study done by Susie Broughton and colleagues, where she looked at 6th grade students and their anger about Pluto's demotion as a planet. When they engaged in critical evaluation, these anger and frustration was ameliorated. It wasn't eliminated, but it was ameliorated. So it makes for a process where the students can be much more, it involves their emotions, it validates what they do, it provides the motivation. So I would argue that we should try. At least we could try it from a research standpoint, see if it causes any problems. But yeah, I know it's a little bit different message, that's for sure. And people are uncomfortable with it, particularly when you talk about biological evolution. But you have to be careful again. You know, it has to be done through this mode of critical evaluation. Students have to know what that means. I didn't actually no, there was very little ambiguity. The students did a great job in drawing the arrows, Tim. And another reason was if you saw the explanation task, let me pull that up for a second here. In the explanation task, I haven't really done a thorough analysis of the actual arrows that they drew. Well, here, let me show that up here. That's not necessarily as important as the explanation task, which is here. And here in the explanation task, they picked 3 of their, what I've defined as the 3 most important arrows that they drew. And they say, well, evidence 1 strongly supports model A because, so they talk about basically what kind of arrow they drew from evidence 1 to model A, and this strongly supports would be a squiggly arrow, and then they explain why. So not a lot, there is, yeah, as you go through this explanation task, that's a little bit more difficult process of trying to interpret what they're saying in these explanations, but not a lot of ambiguity in the arrow itself. So if you noticed, I had, this is the question that Tim is having about IRB. If you noticed, I had 169 subjects. There's about 430 students in the 7th grade total. All of them did the activity because it was all aligned to their science education standards at that grade level and part of their curriculum. So it was totally aligned with their normal curriculum. However, in this process of getting assent and consent, we were pared down from about 440-ish to 169. We didn't have many parents. The parents give consent in this case when you're working with young children. And most of the parents gave consent. The problem was, well, actually I shouldn't say that. Most of the students gave assent. I don't know about the parents not giving consent because I think a lot of them just didn't take the consent form home. So this is a typical middle school student just forgetting it and being brain dead. So, do I think I might have a sampling bias? Absolutely not, because the reason that I think the students didn't bring the consent forms in is because they forgot. It's a simple matter of that. So, and we have some evidence to that. I've written that up. As a matter of fact, that was one of the questions from our peer reviewers on the article that I've written up about this for learning and instruction. So the question is, are better students less likely to forget? Remember, this is a quasi-experimental design, so we should see that in the results, right? We should see some kind of effect here, right? Maybe something here or something here, but essentially they were equal at the beginning. So basically the robustness of the design, I mean, I say it's quasi-experimental, but it was very robust. So it was a robust quasi-experimental design. So the fact that we see that the students were basically the same at all the preconditions means that we probably didn't have any kind of bias. I did some more sophisticated statistics to look for teacher effects, which I don't think anybody's asked a question about. And essentially we found no differences among the teachers. And all the teachers taught it a little bit different. I mean, you do your professional development, but when you anybody that's done professional development knows the teachers make it their own. Well, they all, and when I observed in the classroom, I thought I was screwed. I thought the study was not going to work. Turned out it didn't have any effect at all, that the intervention itself was robust enough that the idiosyncrasies among the teacher did not affect the results. And there's a way to look at that, but they call the unit of analysis. Yeah, and I don't know. You know, we don't know if it was really an assessment. What I've done is because I also was concerned about this question about whether the good students were the ones bringing the forms, and based on other achievement measures that I had, because I was able to access some of their other data, these are pretty much run-of-the-mill students. It's a pretty much homogeneous group, and you can tell that. You can really see that when you reflect on their explanation tasks, that you have a wide variety.
Well, Doug, this has been absolutely fantastic, and we so appreciate you staying up late at night on the East Coast and sharing your expertise with us. I think I speak for everybody in saying that this was exactly the information we needed, helps us understand different ways of attacking a really complex problem, and we think that problems like this are really worth pursuing. And we know that you're just in your first steps and working on this for a lot of time. But we just wanted to say how much we really appreciate you being here.
Well, you're welcome. And